thing I forgot to mention was that this notion is, so we had these three equivalent definitions, remember, in the information theoretic setting, right? But now what we want to also make sure is that the definitions continue to be equivalent, and the notion of semantic security in the computational setting. Semantic security was the one where we were saying that the distribution over the messages doesn't change. So here the notion of semantic security is a bit more involved. So here we say that there's this slightly more involved definition. So let's look at it very quickly. We will not prove that these are equivalent. It's a bit involved. I also don't know the proof actually. I've never looked at it in detail. The special case is done in the book. But what is the definition? So you have the scheme generic deck, and we say it's semantically secure if for every PPT algorithm X, so every PPT algorithm A, there exists a polytime algorithm A prime such that for every efficiently samplable distribution X and all polytime computable functions F and H, there is a negligible function satisfying this. Okay, so H is supposed to be capturing the side information that one might have about the message. So the adversary is given the side information, it's given the ciphertext, and it's given the security parameter, of course, and we wanted to compute some function of the message, right? So that's what we understand by an intuitive definition. So whatever this adversary A is doing, we should be able to replicate that with an adversary A prime that continues to be efficient, given access only to HM, the side information, and the security parameter, but no information about the ciphertext. Okay, so we want this, and the outputs should match, right? So that's what we want. Match meaning up to a negligible factor, right? So this is the semantic security. So it captures the intuitive notion that you should not be able to learn anything about the message, because whatever you could learn using the ciphertext, you could have also learned without using the ciphertext. So for example, if fm is a constant function, obviously any algorithm A can predict what the output of fm would be, but so can A prime without having to use the ciphertext. So that is the semantic security definition, and it turns out to be equivalent to this distinguishability based definition or indistinguishability based definition. Okay, so that was one thing I wanted to mention. Okay, so in the next video I'll tell you how these definitions can be achieved, or in particular at least the indistinguishability definition, and then the CPA and that's it. Yeah, CCA will not.